Well, we're ready to start. My name is Raphael De Lio, and today we're going to be talking about 3 efficient probabilistic data structures: the count-mean sketch, Bloom filter, and TopK. I presented this also at Devoxx UK and Devoxx France, and in both of these conferences I did that a little bit different. I started by giving a little of context in the beginning, talking about how I got into Bluesky, but today I'm not going to do that in such an extensive way. I cut a lot of noise, so I think we can be more efficient. We probably have more time today. So if you have any questions, feel free to interrupt me in the middle and just ask me anything, unless the question is going to take 45 minutes, then it's not doable, right? But basically, let me ask you, who is in Bluesky? Do you know Bluesky? The first question. No? So Bluesky is a social network that is very similar to Twitter. Right, so you have all these short posts that you can basically tweet about anything. Politics, that my manager hates. I shouldn't talk about politics, he said. But also, I don't know, artificial intelligence, technical things, anything you want to talk about, you can talk about in Bluesky. And my journey with Bluesky started in August of the last year, because I don't know if you have heard of that, but Twitter got suspended in August in Brazil. And basically, we had all these Brazilians moving in mass to other platforms, and one of them was Bluesky, and I just followed the lead, and I was also part of Bluesky when they all did so. So basically, you can see in this post that the Bluesky did itself in their own platform on the August 3rd that they had just got new highs and everything, and Bluesky had gotten 1 million new users at the time. So that's how it all started. But Bluesky is quite an interesting social network. First of all, because it's a decentralized social network, meaning that there's not a single entity behind it. So think of it roughly like emails. You have multiple providers that communicate using the same protocol. That's the same thing with Bluesky. So if you're not happy with Bluesky as a provider, you can always move to a different provider or host yourself your own provider and take with you everything that you had in your account, such as your followers, your followings, your posts, even your blogs, because they're public in Bluesky. Besides that, they also offer a very rich REST API that you can use as a hobbyist, for example, or to build analytical tools. Many of these endpoints don't even need authentication, which is pretty cool. And also, they offer the firehose and the Jetstream, which are basically WebSockets that you can connect to and listen to everything that is happening in the social network in real time. People creating accounts, people creating new posts, people blocking each other because it's also public, as I said, people deleting posts, and everything else. And that's actually what I'm interested in today, because one of the many things Bluesky didn't have at the time that I joined was training topics. So I thought to myself, I'm not doing much. Maybe I could create my own training topic. So that's the actual title of the presentation. That was the original title, which was Blooming Training Topics on Bluesky. So I want to ask you these questions now that you probably don't know the answer, so I'm going to answer for you as well, don't worry. But basically, how many posts per minute do you think are in Bluesky today? Approximately 2,200. Doesn't sound like much, but then you think about a month, for example, you're talking about 95 million posts per month. It's a lot. It's a huge data stream, which is very nice for me because I can use it to showcase these probabilistic data structures that I'm going to be talking about in just a few minutes. So how many unique words are mentioned in Bluesky per minute, do you think? Well, approximately 22,000. All right, lots of words that we're going to be counting. And how much memory do I need to analyze this amount of data? Well, if I'm using a sorted set, approximately from the estimations that I did, and that's the funny thing about deterministic data structures, I'm going to come back to that later, 2 megabytes per minute or 1 terabyte per year. But I said that's an estimation because those, like a sorted set, can grow in size dynamically. So if more people get in Bluesky, more people start posting, my data structure is also going to be bigger. So I cannot really predict how much I'm going to be consuming in 1 year, or how much you're going to be spending in money in 1 year using deterministic data structures, right? As I said, Bluesky has 35 million users today. It had 10 million users when I joined. By the end of the year, it could be 45 million. People can be posting more, people can be posting less, right? So what if I had a data structure with fixed size? So once I initialize this data structure, it never grows in size, right? That's where we have probabilistic data structures. So they're very memory efficient. Once they have been initialized, let's say with 500 kilobytes, they're going to be 500 kilobytes forever. right? But before we dive into probabilistic data structures, let's take a step back and remember what are deterministic data structures. So deterministic data structures are those data structures that we work with every day. So maps, lists, arrays, trees, all of these data structures that basically you can insert something into them, and you can kind of be sure that once you try to retrieve this thing back, it's going to be there. So if you add a member to a set, for example, and later on you check if this member exists in the set and nobody else removed it, it should still be there, right? If you add something to a list and later on you iterate through this list, this should still be there. With probabilistic data structure, it might not be the case. So for example, we were talking about sets. There is a similar probabilistic data structure to sets that is called Bloom filter. And with that one, it behaves very similarly. You can add members to it and then later check if those members were added to it. But a Bloom filter, if it tells you that it hasn't been added, you can be 100% sure of that. But if it tells you that it has been added, you cannot be 100% sure. So it might give you false positives, all right? So that's the trade-off, basically, between the deterministic and probabilistic data structures in a nutshell. All right, talking about data structures, I already asked you if you knew Redis. For a long time, Redis was known as a data structure server because of all the data structures that are inside of it. Basically, in 2009, when it was created as a database that was supposed to be highly available and highly scalable and fast, we already had, oh, look at that, so fancy, 4 data structures, and later on we started adding more, including Bloom filters, counting sketch, TopK, Cuckoo filter, tdigest, and hyperloglog. All of those are probabilistic data structures. They're also available there in this distributed data structure server that you can use as an add-on for your applications. Okay, too much talk. Let's talk about building our trending topics now, our trending topic solution. So we're going to go through 3 challenges here. The first one is counting the words, the individual words. The second one is duplicating the messages. And the third one is detecting spikes, so the trendings themselves, right? And for each one of them, we're going to be using a different data structure to do so. For the first one, you're going to be using the counting sketch. For the second one, the Bloom filter. And for the third one, the TopK. Right, so the first challenge is counting individual terms. And we can do that with a sorted set, which is a deterministic data structure, right? So a sorted set. Do you know what a sorted set is? Okay, just a few hands, most hands actually. So it's a deterministic data structure. It stores individual members with a score. It's basically a set with a score next to each member. It grows in memory. So the more elements you add to it, the more memory it's going to consume, basically. And then we have the other approach, which is the counting sketch. Right, so the counting sketch is a probabilistic data structure. It's used to estimate the frequency of elements in a data string. So we have counters. It's used for counting, basically. It's somehow similar to a sorted set with some differences. So for example, you can count elements with a counting sketch, but you cannot know what you're counting there. So with a sorted set, for example, you can retrieve all the members. With the counting sketch, you cannot. So you're going to see it later on as well. But the thing is, it has fixed memory, so once it's being initialized, it doesn't matter if you're counting 1 element or if you're counting 1 million elements, it's always going to have the same size. So very memory efficient. All right, and the trade-off is that it might give you wrong estimations, as you're going to see in the demo after I tell you how it actually works. So the counting sketch, when you initialize it, you basically have a grid. So you have a width with the number of columns and a depth, the number of rows. And it's a grid of fixed size. So if you initialize it like this one, for example, 5 by 3, it's going to be 5 by 3 forever. And inside of each of these slots, we're going to have a counter that is initialized at 0. So let's see what happens when you try to increment a certain term using a CMS. So you're going to create the command cms.incr by the name of the CMS, which is terms, and then the term we want to count, and the number of times we want to count it. So we want to count Redis. Let's issue this command to the database. And what's going to happen is that Redis is going to run a different hashing function for each of these rows. Right? So for the first one, it returned 2. It's going to return a number between 0 and 4. So in this case, it returned 2, meaning that we're going to increment the counter in the 3rd column of the first row right there. Let's see it happening. Okay, so incremented this counter, and you're going to do that for each of these rows. So for the second one, it returned 4, meaning that we're going to increment the counter in the 5th column of the 2nd row. And for the last one, it returned 1, meaning that we're going to increment the counter in the 2nd column of the 3rd row. Those hashing functions are deterministic. So whenever you give a certain term to it, such as Redis, they're always going to return the same numbers to you. So they're always going to increment the same counters. All right. Let's add some other terms to it. Let's count other terms as well, such as pets. So in this case, we're going to run the same hashing functions, but giving it a different term. So for the first one, it incremented the first column. For the second one, it's going to increment the fourth column. And for the last one, you're going to see that we had a hash collision, meaning that we're going to increment a counter that had already been incremented before. So now it's 2, not 1 anymore. I'm going to add other 2 elements so that I can show my point after we try to retrieve some data back. So this time we're talking about cats. So we're going to run the hashing functions again. For the first one, we're going to increment the fourth column. For the second one, it's the last column, another hash collision. So we incremented the same counter. And for the last one, we're incrementing the first column. One thing that I want you to bear in mind here is that we're only keeping track of the counters, right? We're not keeping track of what we are counting there. We're not storing the word cats. We're not storing the word Redis or anything else. It's just the counters that we have in this data structure. Okay? And finally, let's just add one more thing to it, which is going to be dogs. And here, we're going to have a hash collision in the first row. And finally, we're going to increment the second column of the second row. And we're also going to increment the fourth column of the last row here. OK, now let's try to get something back from this CMS. All right, how can you do that? You can do that using the command cms.query. Give the name of the CMS and then the term. You're not counting anything now. And what's going to happen now is that Redis is going to run the same hashing functions, but instead of incrementing the counters, it's actually going to look at the numbers that are stored in this counter. So for the first one, it sees 2. For the second one, it sees 1. And for the third one, it also sees 1. And here's the main of the count means catch part. It's actually going to give you back the minimum number that it sees. So in this case, 1. And it's going to tell you that Redis has probably been counted only 1 time. But now let's see what happens when you try to do the same with, oh, sorry, that was dogs, not Redis. Now we're looking at Redis. So when you do that with Redis, Redis suffered hash collisions in all of the counters, right? So it's going to look at 2 in all of them. And then it's going to reply that, well, Redis has probably been counted only twice, actually. We know that it was only once, right? But given the nature and the design of this data structure, it can give you a little bit of accuracy here. However, this accuracy can be controlled. So basically, when you look at the number of columns, we're talking about the error rate. When you look at the number of rows, we're talking about the error rate. So for a sketch of 5 by 3, as you were talking about there, we were looking at an error rate of 40% and the confidence in this error rate of 99.87%. So we could say that 99.87% of the time, the counter will be within 40% of the true value. So the bigger a data structure is, such as one of 2000 by 10, for example, we have an error rate of 0.1% and a confidence in this error rate of 99.99%. So basically 99.9% of the time, the counter will be within 0.1% of the true value. Let's look at it. Oh yeah, go ahead.
Is this why you use multiple hashing algorithms instead of single hashing algorithm with a row that's 15 elements wide?
Yes, but use multiple hashing algorithms because you want to get a different column in each of the rows. So you increase the confidence in the error rate. OK. So what I did, I created an application. And I ran this application throughout the night. You can, by the end, I have a QR code. You can also run that locally if you want. In this application, we have 4 modules. One is the counting sketch. The second one is the Bloom filter. The third one is the TopK. And the last one is the dashboard. I'm running the dashboard now. And let's come here to the dashboard. And you can see that we have a lot of CMSs that were created throughout the night. All of them have the same size. Is this big enough? 156 kilobytes. Let me zoom in. Oh, yeah, now that's big. And if I open one of them, and let me open one that is the Midnight 44, because I don't know what people are talking about online. And this one I know. So I know that they're not talking about obscene things or things that I will regret showing in the screen and my employer wouldn't like. So let's also open the analogous sorted set that I created here. And you can see that it has approximately 2 megabytes. But most of the sorted sets, they have approximately 2 megabytes here. All right, and now let's look at the data that was returned. The sorted set is actually the truth, right? The sorted set is deterministic, and it's saying that people were counted 106 times. I trust it because I created the application. But if you look at the CMS, it's actually telling us that it was counted 118 times. See a little bit more, but I ordered those by the score, and you can see that even though there is some discrepancy here, they're still quite accurate, right? Especially the elements that are on the top here. So we have people, time, it's, love, Trump, game. And then some start changing. So I'm, so this one is 55, this one is 45. Telegram VIP, day, read, real, play, and so on. Right? So counting sketches, they're not as accurate as sorted sets, but you can see that they consume way less memory in this case, while still giving you a controlled accuracy. So for this use case, it's good. For a use case where you need real precision, it might not be. So you gotta bear that in mind. Also, I wanted to show you this other application that is the Redis Insight. And inside of this application, let me change the database here. You can actually see all of the data structures that were created inside of Redis. And I could open one here, for example, the CMS, and let's open one at random here. And you can see that I cannot see what's inside of the CMS because probabilistic data structures are not supported here yet. But if I looked at a sorted set, for example, and I open one here, I could see the sorted set. I can look at the data structures. I can create new data inside of Redis. This is a nice analytical tool for Redis that you can use as well. Free to use. All right, so that was the first challenge. Let's talk about the second challenge now. But before, there were other use cases that I wanted to talk about. One of our customers, for example, they use counting sketches with their logistics system. So basically, let's say you're picnic or Albert Heijn, and you have all these cars that are traveling around, and you want to make them more efficient, and you want to see where they go and how frequent they go, like into certain streets or certain points in the map. So you can basically, every time they pass through a point, you can count that with a counting sketch. You don't need to be super precise. You just need to know where are the places that they travel the most, right? Without consuming a lot of memory. This is one use case. Another use case is analytics. So let's say you have an app or an e-commerce platform. You want to see how frequent users go to a page. You can also use CMSs to count in these cases as well. But now let's talk about our second challenge, which is the duplicating messages. So the duplicating messages, basically what I want to do here, I'm listening directly to the WebSocket, but I have another demo where I actually use streams to analyze my data. And when you work with the streams, you know that we can consume duplicate messages sometimes. So I wanted to have a use case here where I actually did some deduplication before I consumed the message. The duplication can be done with sets. So basically we add the ID to the set, and then you check if the ID has been seen before. Right? So that a set is deterministic, it stores individual members, it grows in memory. But I could also do that with Bloom filters. All right? So Bloom filters are probabilistic. They're used to test whether an element exists in a set. And it works somehow similar to a set, as I explained in the beginning of the presentation. And they're fixed, and they have fixed memory. Right? And the trade-off is that it might give you false positives, basically. Okay, let's see how it works. It works similarly to the counting sketch, but instead of having a grid, you have a one-dimensional array here. So you're going to create this one-dimensional array, in this case with many slots, and these slots are all going to be bits, and they're all going to be starting as zeros. It's fixed size, so it doesn't grow up in time. So let's see what happens when you try to add a member to a Bloom filter. So let's create the command bf.add stopwords I'm. Stopwords was the first example that I gave using this presentation, so that's why I'm using that here as well. And what's going to happen is we're going to issue this command to Redis, and Redis is going to work with hashing functions again. In this case, it's going to use 3 hashing functions, and then it's going to flip the bits in the positions that are returned. Right? So the 3rd position, the 5th position for the 2nd hashing function, and the 2nd position for the 3rd hashing function. Now let's try to add something else. Let's add the stop word LOL. And what's going to happen is that it's going to run these hashing functions once again. So for the first one, you're going to flip the bit there. For the second one, we're going to flip the 4th column. And now for the last one, you're going to have a hash collision, and you're going to look at a position that was already flipped before. So what are we going to do? We're not going to do anything here. All right, now let's see if something exists. So we can run bf.exist, stop words I'm. We know that this exists. What's going to happen is that Redis is going to look at the same positions for this one. It's one for all of them. And then it's going to say probably it exists in the set, in the Bloom filter, actually. Right? Let's try to see something else, which is devox. Let's see what happens now. For devox, you can see that for the first one, it's going to look at 0. While for the other two, it's going to see 1. In this case, it's going to return that devox has never been added to the Bloom filter. And we can be 100% sure about that because it's 0, it has never been flipped. But now let's see what might happen when you're trying to check if something exists and we know that it hasn't been added, such as Brazil. And then we check here. And in this case, I made it in a way that it's going to look at 1 at all of the bits. And in this case, the Bloom filter is going to say that Brazil probably exists in this Bloom filter, even though we know that it doesn't. All right, let's look at the demo now. So far, so good. Do you have any questions about Bloom filters or the CMS? No? All right.
Doesn't the Bloom filter actually have many rows, and each of the hash functions acts on its own row?
Well, I think it depends on the implementation. The way it's implemented with Redis, it has only one-dimensional array.
And how many bits in that array?
So it depends on how you create it. So when you create a CMS with Redis, you can define the number of columns and the number of rows. But with the Bloom filters, you can. You basically tell Redis how many elements you think you estimate you're gonna be checking, you're gonna be adding to it, and also the probability error rate that you'd like to have. And then Redis is gonna create it for you automatically. What you can also do with Redis is to tell Redis that once a certain number of elements have been counted, so let's say you created a Bloom filter that should count 1 million elements, and you have counted already 1 million elements, then Redis is going to create automatically for you another Bloom filter that is going to work alongside the first one. So in this case, you can see that it can grow in memory because it creates Bloom filters next to each other, so that once you have consumed all of the spots, basically, you don't suffer from that. So this is done automatically for you. If you want, this is optional. But answering your question, it's one-dimensional array in Redis. So let me hide this one, the count min sketch. Let's open the Bloom filters here. And what I did is I have 2 or 3 sorted sets in this case. So we have messages dedup set. You can see that it has 144 megabytes because it consumed, if I'm not mistaken, more than 1 million messages. These are the IDs of the messages, and then I'm going to select the Bloom filter here. The Bloom filter, just like the count min sketch, we cannot know what has been added to it, right? Once you try to query it back, then it's going to tell us if it has been added or not, but you cannot say, oh, what has been added in there. It doesn't tell us. So what I'm going to do is I'm going to copy some IDs here, and what I expect to happen is that it tells us that these IDs have been added to the Bloom filter. So for example, this one. So you see that it says might exist in the Bloom filter. But if I do something else, such as Brazil, for example, and I check it, you see definitely does not exist in the Bloom filter. So you can be 100% sure about that. And I'd like to show you an example where you have a false positive, but it would be very difficult to find one because it's a probabilistic data structure. I cannot know what would actually return 1 for all of them. We could try some words, I don't know, test, or Netherlands. But yeah, it's very difficult to come across a false positive, at least in the way that I created the Bloom filter, that I created it to count lots of elements. What I wanted to show you as well, because I told you that more than 1 million elements had been counted, is this set here in Redis Insight, and you can see here that 1,200,000 elements had been counted using this Bloom filter. It has this set. It consumes 144 megabytes of data, while the Bloom filter that I created is only consuming 3 megabytes of data. So it's analyzing the same data, consuming much less memory here. So this is Bloom filters in a nutshell. Bloom filters are cool. They're used inside of databases, for example. But other use cases that you can have for it is, for example, username availability checker. So you have a website. Oh, sorry, go ahead.
I was wondering, is there some kind of hard link between the size of the Bloom filter and the performance benefits compared to the size of the set, for example? I mean, of course, you use more memory in the set, but for the set you only have one hash call, and for the Bloom filter, depending on the size, multiple hash calls. Is there some kind of quick?
That's a good question. That's true. So with a set, it would be constant time. With a Bloom filter, it's going to be okay. So depending on the number of hashing functions, indeed. So it might be a little bit slow in that sense. That's true when compared to sets. And another thing that I wanted to mention before we continue, now that you asked this, is about the CMS as well, right? Because the counting sketch, as I told you before, we cannot see what's inside of it. We cannot know what was added, right? With a sorted set, it's very efficient to basically get all the elements that were inserted into the sorted set and also sort them because they're already sorted for you, right? But with the CMS, what I had to do was basically create a set with all of the words, so 5 million words, and then I had to iterate through each of these words, and then for each of them, I went to the CMS and I queried them back. So you can see that it can be much less efficient if you're using a CMS for that purpose. But then you have another data structure that is a TopK that might help us with that I'm going to showcase as the challenge number 3. So you see there are places where you want to use it and places that you don't want to use it. It might help you. It might create you problems. So going back to the presentation. So the username availability checker. So basically when you try to see if a username already exists when you're signing up in a certain website, what you can do to be fast and not consume a lot of memory is basically use a Bloom filter and check if a username exists, and it can give you a false positive, and the person can just choose another one. That's okay, right? Another cool use case is actually from Google. So basically they have to index trillions of pages, and they would to have a set with trillions of elements inside. And instead of doing that, they have Bloom filters, and they use Bloom filters to know if they have already indexed a page. Sometimes they can come across false positives, and I don't know what they do in that case, but they probably come across the same page multiple times, and Bloom filters also help in this case. That's actually a very nice question, because I was thinking about talking about speed efficiency during the talk. But compared to this data structures, deterministic data structures, they didn't really make sense, because those are already quite efficient. Going back now to the last challenge, which is tracking spikes. So for tracking spikes, what I wanted to do was actually look at how many, what the average the words had shown up in the data stream in the past, let's say 5 minutes, and then compare to the current frequency of the words in the current minute. And doing that, I could see if it was basically the same frequency from before, or if it was actually trending, if it was actually spiking. That's what I was trying to do here. And to do so, I would have to store all of the words in a sorted set with their scores. And I have already talked about the sorted set, deterministic, and everything else. Or I could use a TopK in this case. A TopK is very similar to the counting sketch. The difference is that here we're telling the data structure that we want to keep track of the, let's say, the 5 top elements or the 10 top elements of this data stream, or the elements that we're counting here, right? So it's also fixed memory, might give you imprecise results, but it's very memory efficient. Let's see how it works. The TopK can be a grid as well, but it can also be a one-dimensional array. And for the sake of the example here, I'm going to use a one-dimensional array. And what I'm trying to do here is find out what are the 5 top elements in this data stream, right? So I created that with 5 slots. So that's a TopK of 5. When you create it, you also give it a decay, as you can see here. In this case, I gave the default one, which is 0.9, which I'm going to show you how it's used later on. So let's see what happens when you try to add something to the TopK. So we're trying to count Redis. Let's issue this command. The TopK is going to run one hashing function in this case. and it's going to store the counter in the second slot because 1 was returned there. So we're counting Redis in the second slot. Now let's try to count something else. In this case, devox. Hypothetically, because I wanted, it returned 2. So we stored that in the third slot there. Let's count devox one more time. So increment that counter again. What's going to happen now, and it's been happening actually all the time, is that what Redis is doing is looking at the slot where you're storing that and seeing, is there anything already there? If there's nothing, we're just going to store. If there's something, we're going to check, is this me? If this is me, if this is what we're trying to count, we're just going to increment the counter. Otherwise, as you're going to see what's going to happen now, when you try to increment Java, what's going to happen is that it's going to return the same slot of devox. So what Redis is going to do is it's going to check, is Java that we're counting there? And since it's not, instead of replacing that, we're going to use the decay, and we're going to multiply the decay by the number of times devox had been counted. It's going to return 1.8. We're going to floor that down to 1. And now this is the new number of times that devox was counted. All right? Now let's try to count Java again. So what's going to happen now is that the hashing function is going to return, because it is deterministic, the same slot. Now we have 1 for devox. We're going to multiply that by the decay. It's going to be 0.9. We're going to floor it down. 0. We're going to remove devox, and we're going to add Java in its place. So you can see that we added Java, we removed devox, even though we still had 3 slots available. All right? And even though devox was actually counted more times than Redis. You see, so that's why it might be imprecise. Of course, it's optimized in the algorithm inside of Redis to use all slots and to be optimized for that. But in the example, I just wanted to show what might happen. All right, so this is what I had explained to you before, that I wanted to look at the average of the past 3 minutes, for example, and compare it to the frequency of the current minute, give it a score, and add this score, which would be 0.5 to the TopK. Let's look at the demo. This is a cool one, because as I said, I had this running throughout the night. And well, what I saw in the morning wasn't very pleasing, because people talk about things like obscene things and things that you don't want to see in a presentation like this. So I checked this one first, midnight 44. This is actually midnight 45. Yes, that's a good one. So you can see that all of the TopKs, they have the same size, 283 kilobytes. And the TopK said here for the top 10 or 15, no, 10, yeah, that performance in Spanish was counted 26 times, walk power 25 times, set hard 25 times, and so on. And now let's open the analogous sorted set. So you can see that the sorted sets vary in memory very much for bugs that I created in my application, but also because of the size of the data set. So midnight 45. And you can see that this is actually the truth. And if you compare them without looking at the scores, you can see that it's quite similar. So the first one is performance in Spanish, and then those are all 25. Walk power should be here. Walk power is not here. Is it there? Yeah. Yeah, okay, it's here. Sad Heart, SF6 season. So my TopK is working very well. It's very precise because I created it very big, probably. So I could have even, yeah.
Yeah, I have a question. So basically, both TopK and sorted set are using the heap under the hood, right?
Yeah.
But how it is possible that the sorted set is really loading some memory? Like, what is real performance boost here?
So basically, if I understood your question correctly, in the sorted set, I have to store all of the elements, right? So if I had seen 1 million words, I'm going to have to store all the million words there so I can sort them after I have stored them there, you see. With the TopK, I don't have to store the million words because it's always removing what's not the trending at the time. Was that what you're asking?
Yeah, well, actually, yes.
Okay. But that's basically why it's more memory efficient, because you only have 5 positions, while for the sorted set, you would have to look at all of them and then sort them afterwards.
This boosts only the memory, the space, basically.
Yes.
But according to asymptotic analysis, which one is faster?
In this case, if I'm not mistaken, this is the TopK, and we can actually confirm that.
Because both of them recalculate the tree each time you add a new element.
Yes, when you add an element, the TopK might be slower, but when you retrieve the elements, I think it's faster. So this is the documentation of Redis, and a cool thing here is that you can actually see the query list and anchor by. Those are the ones I'm looking at.
Do you have Wi-Fi?
Oh no, let's connect to my phone really quickly. Okay. Nice. So you can see that the query, when you're actually asking for individual elements, it's ON, number of items. The list, okay. Yeah. And I think that it's very similar to the sorted set, actually, because the sorted set
Should be the same, right?
yeah, I think it's O log n and then z. Oh, so this is the z score when I'm getting only one member. So this is O1 because I'm using the I know which member I'm looking for. But then you have z range, and that's what I do to get all of them. Yes, and that's O log n plus m, where m is the number of elements returned. So if you want to return all of them, or just 10, for example. So yes, it's more memory efficient, but it might not be more performant. Should be most of the time, depending on the data structures that you're using. But Redis is already optimized for performance and memory as well. So, okay. Going back here, where was I? All right. I just wanted to conclude, and to conclude now, it's quite interesting because with probabilistic data structures, I can kind of predict how much memory you're going to be using after a year because they're like fixed in terms of memory. But for deterministic data structures, I had to kind of estimate, right? So on the left side, for deterministic, I'm estimating. And for the CMS, I actually calculated. I can kind of be sure with the data that I had. So you can see that for counting individual terms, for the CMS, I would be using 80 gigabytes per year. And for the sorted set, 1 terabyte per year here. For the duplication, 1.2 gigabytes per year for the Bloom filters. As I said, because I'm going to be creating more Bloom filters as my data grows. And also for the set, 1.3 approximately terabytes per year. And for tracking spikes, 288 gigabytes per year. And for the sorted set, 1.3 gigabytes per year. So you can see those data structures might be much more efficient in terms of memory. But as Venkat said 2 days ago, have the knowledge and the wisdom to know when not to use it as well. So they might be very good for your use cases, but they might also be terrible for your use cases. So now you know how they work, and you can decide by yourselves if it makes sense to use in your applications as well. My name is Raphael De Lio. I've been working as a developer advocate for Redis for the past 7 months. Before that, I worked as a software engineer for the past 7 years. I worked with this guy. I worked with that guy there as well, Niels. So many familiar faces, which is pretty cool. And, well, I also have a YouTube channel where I talk about Redis. I also talk about Redis at the Redis YouTube channel. There's the QR code where you can find the slides, the repository, links to the YouTube channel, everything else. As always, stay curious. And before we finish, do you mind if I take a selfie with all of you? Is that okay? Cool. It's just, I got to prove to my boss that I came, right? Not just, okay. Perfect. Thank you very much.